Okay, so welcome to Chapter 3. In Chapter 3, we're going to be introducing the topic of image transforms. These are specific operations that are linear, that we apply to images to map them into an alternative space where the representation in the alternative space provides us with some useful properties for inference, for representation, and for doing other things. So now, because we're dealing with images, we're going to be looking at starting to make a connection with classical Fourier transforms applied, well, I should say one-dimensional Fourier transforms or Fourier transforms of one variable. For images, we deal with Fourier transforms that are functions of two variables, so x and y spatial coordinates. Later on, we'll look at discrete Fourier transforms, but what I want to do first of all is to make a connection between topics you will have met elsewhere, which are effectively one-dimensional Fourier transforms, or just making a link with one-dimensional Fourier transforms. Sorry, it's a bit clumsily stated, but let's move on to looking at that. So I'm going to drop to my board, and my open board has dropped off for some reason. Let's get the board scene back up. So open board. Should be that one. There we go. Good. Okay, so let's think about the definition of a one-dimensional Fourier transform. So I'm going to start by thinking about, first of all, a signal. Let's take our signal as a function of time. We're going to represent as f of t. And that f of t is simply going to be some kind of amplitude that varies as a function of time. So there's our time domain axis, and we've got some signal, some waveform or signal that varies as a function of time. So that's our f of t. So we call this a time domain signal. So by time domain, we mean that we have a representation that's an amplitude as a function of time. Okay, now one of the definitions for the Fourier transform is, so it's quite commonly used in the field of signal processing. So different definitions are used, or let's say conventions are used in different fields. But one of the convention that we're going to use is this one. And you probably have met something like this before. So that should be t equals plus infinity, t equals, right, okay. F of t, e to the minus j omega t, and then we integrate that in t. So this is the definition of a Fourier transform, where there's our signal, varying as a function of time. And then this thing here, we refer to as the Fourier transform kernel, or the kernel of the transform. The kernel contains a function of omega and a function of t. So this t here is, if you like, linked to this t here. So as we move through f as a function of time, what we do is we compute this value here, e to the minus j omega t, multiply that by f of t, and then we continually do that and then integrate the result under that product, or if it's a product curve, if you like, over all time from minus infinity to infinity. Because we're doing a definite integral here across the entire time axis, then after we perform this operation, the result, the variable t disappears. So what we're left with, however, is a function of omega. And so for one value of omega, we get a scalar result. But because omega is also present in the kernel, and omega is the Fourier transform variable, often known as the frequency variable. In this case, it's called angular frequency. Then the result of this is going to be a function of omega. So we effectively, when we do this, we're computing an infinity of integrals and producing a result that tells us how this integral changes as a function of omega. So that's effectively what a Fourier transform does. And for those of you who've done the signal processing course, you will probably have come across that this is as you vary omega, you're effectively looking at different frequencies of sine and cosine waves. So one thing that is useful to bear in mind is that the term e to the minus j omega t can be represented as a real, it has a real and imaginary part. So cos omega t plus j sine omega t. So we are effectively multiplying our signal by this complex signal, e to the minus j omega t. Oh, by the way, that should be a minus sign there. So that's a minus, because this is a minus here. And conversely, e to the j omega t, just for completeness, if we flip that sign to positive, will be this. So that's a relationship. Well, that's how to interpret this e to the minus j omega t. It's got a real and imaginary part. Okay, so this is called the kernel, and we get something that's a function of omega, where omega is our frequency variable, or sometimes can also be called the Fourier variable, but that's rare. However, when we perform this mapping of f of t into f of omega, we sometimes refer to f of omega as being in the Fourier domain. Let's draw a line through there. Okay, so this is called the Fourier domain. So that Fourier domain representation is equivalent to a representation of f of t in the time domain, in the sense that if we map f of t into the Fourier domain, we are guaranteed to be able to map back to the time domain. So knowing a signal, or specifying a signal as amplitude versus a function of time, or Fourier domain representation, which is the amplitude of, so this is a complex quantity, it's a complex valued function. So knowing the complex value of f as a function of omega also completely specifies the signal that we've started with in the time domain. And there is in fact a way to go backwards from the Fourier domain to the time domain, which is given by this. So f of t is equal to 1 over 2 pi integral, and now we integrate in omega from omega equals minus infinity to infinity, so over all possible angular frequencies, and we take f of omega, and now we have an inverse kernel, which is e to the j omega t, and our integration is in omega, no longer t. So that, of course, will get rid of any term involving omega, and we get back to an expression involving f of t, back to our time domain. Okay, so let's jump back to our two-dimensional. So once you've reminded yourself about this, the one-dimensional Fourier transform, you can now see that the two-dimensional Fourier transform. Here we've got the equivalent of frequency variables, or angular frequency variables. Instead of being omega, we now have two variables, u and v, so they take the place of omega. You can also represent these by omega x and omega y, so that's sometimes used as a notation, omega subscript x, omega subscript y, but I've used u and v, generally speaking, in the lecture notes. So here are continuous function over space, intensity over space, or luminance over space, is now multiplied by a kernel which consists of two separate separable terms. So, whoops, sorry, the kernel stops here. Sorry about that. So from here to here is our kernel. So e to the minus j ux plus e to the and times e to the minus jvy. So our kernel can also be represented by e to the minus j into ux plus vy. Okay, so because the exponent term is separable like this, so you can take a product of exponents can be handled or mapped to, or is equivalent to the exponent of sums of individual terms. Okay, so that maps us from spatial domain into two-dimensional Fourier space. So this is 2D Fourier space, or 2D Fourier domain. And you can do an inverse mapping as well. So if you start in the Fourier domain FUV, you can find the inverse Fourier transform represented with that notation by 1 over 4 pi squared, and now you're integrating in u here, and you're integrating in v here. So you've got a double integration here of FUV, and now you have the inverse Fourier transform kernels. Same thing you do, you get rid of the minus sign in the exponent, and that gets you back to f of xy. So that's the continuous, two-dimensional continuous Fourier transform. Now, the two-dimensional continuous Fourier transform has some interesting properties that are inherited, if you like, from the one-dimensional Fourier transform. And so if we have two functions of space, so imagine we have two separate luminance functions over space, f1 as a function of xy and f2 as a function of xy. If we have a weighted summation of those two, so we weight the first by a constant alpha, so this is alpha is a constant, and beta is also a constant, then the Fourier transform of the weighted sum of those two fields is the weighted sum of the individual Fourier transforms of each field. So that is known as the linearity property of Fourier transforms. So you have a similar thing for one-dimensional transforms as well. Okay, if we now look at another property, so with one-dimensional Fourier transforms, if you shift a signal in time, so you shift it, you delay the signal, or you advance it in time, make it, so it happens earlier in time, then that's called translation. And the translation in the spatial domain, so if we translate in x and y by an amount alpha and beta respectively, so here we're taking an image and shifting it around in space, what happens is that shift, whatever that shift is, gets localized into what's called the phase terms of the Fourier transform of the unshifted signal. Well, it becomes a multiplier, a complex valued multiplier of the Fourier transform of the unshifted signal. But the important thing is that these two terms here have a magnitude of 1 because each of these is a cos plus j sine, and each of those has a magnitude because a magnitude is, so if you think of them as complex numbers that vary with u and v, and with beta and u and alpha and beta and v, then these things always have these two terms here. Each of these two terms has a magnitude of 1 because cos squared plus sine squared will be the magnitude of a complex term, will always have a magnitude of 1. So the only thing that this does is it changes the phase of the result, which means that we'll look at this later on, but the way that we add up the basis functions we weight basis functions with the same amount but shift them in a slightly different way. So that'll become clearer when we get on to discrete image transforms. Okay. Finally, we don't have this in the closest thing to this in one dimension is actually going to be time inversion. But if you in two dimensions, you can rotate things as well. That's another type of transformation that you don't really naturally have in one dimension. But you can rotate things in two dimensions in the plane. And if you do that, then the Fourier transform of that rotated image becomes a rotation of the Fourier transform of the unrotated image. So that's a nifty property of Fourier transforms in 2D. It also turns out that taking a partial derivative, because if we think about a luminance field as being a function of two variables x and y, we can think about taking partial derivatives of that spatial field with respect to each of the variables. So if we take a partial derivative with respect to x, it turns out that we multiply the Fourier transform of the original spatial field by the term minus ju. So that changes with the value of frequency, but it's a fairly straightforward operation. And so the nice thing is that also if we take higher derivatives of higher order partial derivatives with respect to x, we simply keep on multiplying by ju. So the second order partial derivative with respect to x will have another multiplier of minus ju, and so the j's become a minus 1. The minus multiplications cancel, and you get a minus fuv. And similarly, if you take a partial derivative with respect to y of f of xy, you simply multiply the Fourier transform by minus jv. So these are all really nifty things. And then finally, you may remember that in one-dimensional time Fourier transforms, if you take a signal that varies over time and you shrink it down in time, it's in the Fourier domain, it expands, and vice versa. If you take a signal and spread it apart, so stretch it in time, which is called time dilation, then in the Fourier domain, it shrinks. Now, in the two-dimensional case, you have a similar relationship. So here, alpha and beta are not equal to 0. If alpha or beta are greater than 1, then we take an image and we basically shrink it down in space. If we make alpha and beta between 0 and 1, so not 0 and not 1, but actually in between 0 and 1, so they're fractional, then what happens is we have a spatial dilation. So we expand the image in space, and the result, we have the converse result in the Fourier space, plus we have a scaling of the amplitude by 1 over whatever the scale factor is, 1 over magnitude of alpha beta. So here, this is what gives us the inverse result. So contracting in the spatial domain expands in the Fourier domain, and expanding in the spatial domain contracts in the Fourier domain. Okay, the final property to think about is that in the two-dimensional Fourier space, there's also this thing, which is that if we, so this here is not multiplication, this is convolution. Okay, so it's not multiplication. But somewhat confusingly, what happens is if we convolve two signals to functions of space, then the Fourier transform of that convolution will be a product in Fourier space of the individual spatial fields. And similarly, there's an inverse convolution equivalent, so that if you multiply two spatial fields together, then the Fourier transform of that will be, so there's a constant factor scaling, but the Fourier transform of that, in essence, will be the convolution of the two individual Fourier transforms. So this is conv, not multiplication. Okay, so here the convolution operator is explicitly defined like this. So again, that's convolution. And this is convolution over two variables, or two dimensions, let's say. Okay, so what you do is this is the convolution integral. So you introduce a couple of dummy variables for the two different to replace x and y. So this, we're convolving here in x and y, and so we introduce alpha and beta as dummy variables. So the convolution between these two is this integral here. So note that we introduce the dummy variables alpha and beta, and into function 1. So function spatial field 1 becomes a function of alpha and beta temporarily. Key thing here is that function 2, so spatial field 2, now becomes a function of minus alpha and minus beta. So what we do is we take two spatial fields, and for one of them, we're multiplying them together, but for one of them, we flip it this way and then flip it this way. So we flip it twice. We make it we change the spatial coordinates in x and y so that we invert in x and invert in y. So to see that, you just hide the x and y for the time being. So you have f1 of alpha beta multiplied by f2 of minus alpha minus beta, okay, assuming x is 0 and y is 0. This is a specific case, in which case you're taking one spatial field, flipping it this way, flipping it the other way, and putting it on top of the first spatial field. Let's do it like that to remember we're inverting. Then multiply things together, so you get a product function, and then you find the area under that, which is what you're doing when you do the integral in alpha and beta. Okay, and then you do that as a function of shifts x and y to that flipped second spatial field. So what you're doing is moving the spatial field after you flipped it. You move it back and forth, up and down for all possible shifts in the x and in the y direction, and then your result of convolution becomes a function of x and y. Okay, so result is a function of x and y. Okay, so convolution gives you a function of whatever the original space is that you started off in. Okay, let's move on to the two-dimensional discrete Fourier transform now, which in some ways this is easier to understand because we can always do a calculation that involves a really small image and try to work our way through the calculation. But the definition of the two-dimensional discrete Fourier transform at first glance looks horrid, but you can deconstruct it and you can simplify it so that you get an intuition about what's going on with this equation here. So first of all, let's go through the definition. So instead of having continuous variables u and v, we now have discrete variables. Which are uk and vl. And here, these are discrete because we allow the variable k and the variable l, we treat these as being indices. So they can be thought of as indices into arrays. And you see here that I allow k to take values from 0 up to 1, 2, 3, and so on, up to large M minus 1. And little l takes values, that looks like a 1, but it's an L. Little l takes values 0 up to n minus 1. Now here, fmn is our image. And so fmn is of size m rows by n columns. Okay, so it's a large M by large N image array. And so the and the result of the Fourier transform, because k and l take values of 0 up to n minus 1 and l up to 0 from 0 up to n minus 1, the size of this thing is going to be the same in terms of array dimensions as the size of the original image. So f, I'll just write it here. So f, capital F, is also of size m by n, but generally speaking, f will be complex valued. And the reason for that is because the kernel here of the discrete Fourier transform, so this is the kernel, and it looks, as you can see, similar to the kernel for the two-dimensional Fourier transform all the way back here. Okay, but here we had u of x, so spatial coordinate x, and variable Fourier transform variable u, spatial coordinate y, Fourier transform variable v. If we come over here, we see that instead of having x, we have a little m. So m matches with the row coordinate, and then we have n matching with the column coordinate. So these are not quite x and y, because remember that the x and y positions for Cartesian coordinates are swapped with the mn if you think about your directions as being horizontal or vertical. But this is the conventional way that we use for defining the two-dimensional Fourier transform. So here, m runs through the rows again, and n runs through the columns, and uk and vl will be our discrete Fourier variables. So uk, note, is given by this 2 pi little k over m. So you can write everything in 1 in the kernel, but that makes the kernel very difficult to perceive. So I can expand the uk to be 2 pi little k over large M. So in some books, if you look up the discrete Fourier transform, you'll see that version with the uk expanded out. Same for the VL, but I think this is here it's easy to see the relationship to the continuous Fourier transform. Now, just as we have the forward and inverse transform for the continuous spatial domain case, f as a function of x, y, we also have an inverse discrete Fourier transform for the two-dimensional DFT, and it's known as the two-dimensional inverse discrete Fourier transform, unsurprisingly. And it has this inverse scaling before it, so 1 over large M, large N. And here you can just see that the kernel looks very similar to that of the inverse continuous Fourier transform. We simply swap the sign on the kernel for the forward from the forward transform. And instead of summing, here we're summing over all the rows and all the columns of the image weighted by the kernel. Here we're summing over all the values of uk and vl effectively, but indexed by little k and little l. Okay, so that gets us back to fmn. All right, so the definition of the definition of the forward and inverse discrete Fourier transform is such that if you program these up, and specifically because you've restricted the values of discrete Fourier space to be the same as the number of values of forward Fourier space and the number of pixels in the image, large M and large N, and the way you've specified the kernel functions and sampled the kernel functions, then the two-dimensional inverse discrete Fourier transform of a two-dimensional forward discrete Fourier transform of a 2D digital image returns the original image to within machine precision. And that to within machine precision refers to the fact that here you've got to work out cosine and sine terms to explain or to work these complex exponential values out, to write them out or to evaluate them. And when you do that, you have a certain amount of rounding error. But this basically is designed to get you from image space into discrete Fourier space and then back again with almost no error. So let's have a little look at what that looks like. So here is a demonstration of a two-dimensional discrete Fourier transform. So here's me loading an image. Oh, by the way, here's the FFT routines are actually so fundamental that they're part of the NumPy standard Python package. And I've imported the two-dimensional forward Fourier transform and inverse Fourier transform, and a useful utility function called FFT shift, which we'll talk a bit more about in the practicals. I go through this in quite a bit of detail. But here's us running through getting an image. Oops, and displaying it. So here we are. So here's the image, and the first thing, as I mentioned before, the image here is denoted little xg. That's our little x little g. That's our image. And so it's, if I use the command is complex to see if any terms in this contain imaginary parts, the answer is no. So it's a purely real valued intensity image. Here I'm computing the discrete Fourier transform. And here I'm showing the inverse discrete Fourier transform. Now that looks remarkably, this is the result, it looks remarkably uninteresting. But actually there is something to be seen there. And in order to, so what happens here is that the most important values in discrete Fourier space of capital X, capital G, so please be careful with that in reading this, are located in the top left-hand corner here. And there's a little utility function that shifts those values into the middle of discrete Fourier space, which is called FFT shift. So I'm going to call FFT shift so that we apply that. And you may or may not be able to see, there's a little dot here in the middle of the image array space. So I'm going to show that in a little better detail by using a little utility that I wrote to do this. So this doesn't always work. So what happens is there's an external viewer that you can get in Matplotlib, which gives you some utility functions to zoom, and so those utility functions are shown is shown here. I'm just going to find my right, and so with that utility function, I can, if you look at the bottom right of this screen, you will see that I get the values. I get a spatial location of where I am. It says XY, which is a Matplotlib pathology. So it gives me a location in space, but also gives me a value. And so you can see that the values in there, so this has a value of 1 times 10, so it's of that order, it's rounded off. So I've got values 40, 10, 80, 70, 50, 60. As I get closer to this dot, the values will start to gradually go up. So now I've got values in the thousands. Now I've got values in the hundreds, still thousands. And as I get really close to the center here, I'll get values in the tens of thousands. Okay, so in fact I can zoom in to this bit of space. Let me try to zoom in here. And is that zooming? Or is that not? Oh yeah, that should be zooming now. Oh wait, let me do this. Right, so sorry, I'm just drawing a box around to zoom. So here you can see that in the center of this shifted discrete Fourier space, I actually have a very big value, 1.6 by 10 to the 5, so it's really big values. And they drop off really quickly as I move away from the center of discrete Fourier space. Okay, so that's to do with the fact that, remember I talked about dynamic range in an earlier, let's see if I can zoom out here, sorry. I can't remember how to zoom out. Okay, so the fundamental problem here is that I have a very big dynamic range. Oh, actually, I can go back to my notebook here to talk about this. So, okay, so I have a very big dynamic range within this two-dimensional array, and because of that, when I do my so in my display, my physical display has a limited dynamic range, and what my software environment is doing is mapping everything that's in the image here, or this array here, to fit into the smaller dynamic range of the screen. So if I have a very big range between the biggest value and the smallest value, and I guarantee that the biggest value has to fit, then what happens is that all the smaller values get squashed down, and so that's why everything else appears to be black or zero. So there is a little dot in the middle here on the screen, but it's almost impossible to see. So by the way, the value at the biggest value is this is what the biggest value is in the array. It's 1.68 by 10 to the. Oh, that's not quite right. That's that can't be right. No, that's the DC value. No, that is the biggest value. Yeah. So it's 16,000. So it's quite large. So let me just double check that actually. I think that should be right. Yeah, that's the biggest value. So you'll explore this a bit more in your practical, but so this value at 0, 0 in unshifted discrete Fourier space is effectively the sum of all the pixel intensities in the image, which will become clear in time. Now, one of the tricks we have to display this big dynamic range is to squash it down. And so this is the result of displaying the log of the absolute value of the shifted discrete Fourier space. This is just a way to visualize what's in discrete Fourier space. We very seldom, if ever, use the log of discrete Fourier space to see anything. But if we have periodic structures in our image, they will sometimes show up as visible in discrete Fourier space, and sometimes you'd use the log. So the purpose of using the log here is simply to squash the dynamic range between the biggest value in the array and the smallest. It's purely for visualization purposes. Okay. Now, as I said, there is information in this image, though we can't see it. And if we take the inverse discrete Fourier transform of that XG result, so inverse two-dimensional discrete Fourier transform, and then plot that, we get back the original image. And there is virtually no difference between this image and this one. However, when we take the inverse discrete Fourier transform, very often the result xg dash, as indicated here, will be complex valued. In fact, if I do is complex, I can't remember what the result is here, xg dash, it might actually show up as either real or complex. I can't tell you what the answer is. What? Oh, np dot is complex, sorry. Yeah, okay. np dot is complex. xg dash. Right, there we go. Okay, so it thinks that this is complex valued. In fact, any non-real values at the end of this result are, so any imaginary values are just due to round-off error. They're vanishingly small. In fact, if we look at xg dash, just take a couple of values at random, xg dash, let's say take values 10, 10, just something at random, and see what it is. So it's 0.6 was a real value plus 7.4 by 10 to the minus 17. So it's tiny. This is just due to round-off error. So Matplotlib, neither Matplotlib nor NumPy is clever enough to know that that really is a real valued thing, and this is just round-off error, which is fair enough. So that's why I took the real values to show this. Otherwise, you'd get an error, since Matplotlib imshow won't know how to show a complex valued image. Okay, so that's it for our little demonstration. So next we're going to move on to look at how to interpret this horrible looking calculation here. It's just some other Fourier transform results. We're going to look at how to interpret this this very specific calculation for forward and inverse discrete Fourier transforms using a simplified notation in which we abstract away all those horrible exponentials, and introduce the idea of general linear transforms, which can be applied to two-dimensional images and which generalize the process of understanding a discrete Fourier transform. So when you generalize the operation of the discrete Fourier transform, you actually begin to strip away all those very difficult to understand things, and it begins to make sense. What you're doing begins to make a lot of sense, and you can really put an intuition over what's going on when you move from image space or discrete image space into discrete Fourier space.